Nowadays, the big megacities are mainly located on coasts due to their strategic position. A quarter of the world's population is therefore directly threatened by rising sea levels. This phenomenon now concerns us all, but it is intensified in cities such as New York in the United States, Rotterdam in Europe, and Singapore in Asia. Today, Rotterdam has become the economic heart of the country, and its port is the largest in Europe, a key point of globalization where all our goods are constantly in transit. But the city has an Achilles heel, as it is located 6 meters below sea level. A vulnerability it was painfully reminded of 70 years ago. It's January the 31st, 1953. Off the North Sea, a violent low-pressure system triggers a brutal storm that hits the country's coasts. Powerful winds are blowing at 160 kilometers per hour, causing the water to rise more than 4 meters. The water floods nearly 10% of the country's surface area. Thousands of people are evacuated, but 1,800 of them do not manage to escape from the most catastrophic seaborne disaster Europe has ever known. The government then decides to set up the Delta Works, a gigantic battle plan led by an army of scientists and engineers in order to review its entire defense strategy. Over a period of 40 years, they build hundreds of kilometers of giant dikes, like sentinels of stone and concrete facing the sea. The mast-line keyering is the last major element of the Delta Works. Completed in 1997, this technological jewel is now the largest, most sophisticated and most famous storm surge barrier in the world. It is 420 meters long and 20 meters high, which is 100 meters longer than a lying Eiffel Tower. A steel monster that functions as 2 protective arms for the city of Rotterdam. The Dutch, whose territory is partly under sea level, the same as in Singapore, have developed a large-scale protection system. In the last 400 years, they've become the world's experts in dike technology. Over the centuries, they've built 22,500 kilometers of dikes, the equivalent of the Great Wall of China. With global warming and rising water levels, new methods are being developed to identify the slightest breach that could be fatal to the city. It is here, 300 kilometers north of Rotterdam, that scientists are developing a new high-tech method of observing dikes using hypersensitive sensors.
Ja, dit is dan zo'n locatie waar we dan pijlbuizen in hebben geplaatst. Net zoals wat je daar zo ook ziet bij de binnenteen. Ja. Hier hebben we waterspanningsmeters in zitten. 2 niveaus. En daar bij de binnenteen ook. Ja. Is er maar 1 op maaiveldniveau van het achterland en 1 dieper. Ja. Daar is er nog een kleilaag tussen zit.
These intelligent sensors implanted in the body of the dike are comparable to a stethoscope that listens to the heartbeat of the structure and tracks its behavior in case of damage. This wave generated by the sensor is like an electrocardiogram of the dike. Risk management engineer June11 analyzes these graphs every day for anomalies.
This measures the pressure of the water. Actually, it gives the idea to how high the water might rise because of the sea level you have here. And that is very important to know about the water level you might have in the dike. And that's for the stability of the dike.
This advanced technology is also fundamental to improve the morphology of the dikes, which are traditionally made of clay.
Many dikes are made of a clay dike, which was the old one, and now then sand on top of it or behind. And on top of the sand we have a layer of clay of about 1 meter thick, which is once again protected by grass to keep that from erosion by rain. And these dikes are about, say, 60, 70 meters wide. Now, as you can see, it's very large, but we need that because, you know, when there's a storm, the water goes up very, very high, and we have to keep the hinterland dry.
Today, the general situation is worrisome. If the water level continues to rise at the current rate, the dikes will no longer be able to protect the country. It is therefore necessary to build higher dikes and to raise the existing ones. In Asia, the tiny city-state of Singapore is particularly threatened by the rising waters. On the other side of the planet in Singapore, to fight against the rising waters and its deadly impact, scientists are trying to save some very valuable plant areas. Amidst the skyscrapers, noise and urban frenzy, Berlayer Creek is home to the last small patch of mangroves on the main island of Singapore. For researchers such as Dan Fries, geographer and expert on the coast and mangrove forests, the city is a paradise. Of the 60 species listed in the world, more than half are concentrated in this small area. Brej van Wessenbeek is a specialist in ecosystem analysis. In the laboratory's greenhouses, she is currently studying the properties of the mangrove against tides and storms. She has chosen to grow the two most widespread species in the world to submit them to new experiments.
We know very little how they function under extreme conditions, so with higher waves. So, for example, during a hurricane or a tropical storm, they are then especially important in reducing wave impact, but it has not measured how much they can then reduce, or if they break, or if they get uprooted.
While waiting for the mangroves to reach full maturity, Brej tested the impact of waves on artificial replicas. But so far, her conclusions are not necessarily encouraging.
Many countries in Asia and Africa, they start looking at mangroves as an important buffer to buffer against sea level rise, but also against storms. What I see is that they actually overestimate what mangroves can do. So, for example, in Asia, they have many policies where they say there should be a mangrove greenbelt of 100 meters wide. But what we are now finding from computer modeling exercises is that 100 meters, actually for bigger waves, is way too little.
In a few months, she will be able to conduct her experiments on full-scale mangroves and subject them to what Deltaris is known for, the delta flume. This unique basin is 300 meters long, 5 meters wide, more than 9 meters high, and contains a reservoir of 9 million liters of water. Today, the master of the water is Pim van Steen. He works on coastal areas, and more specifically on dike erosion. In this temple of technology, the largest artificial waves in the world are generated thanks to very powerful machinery.
So behind me we have the wave generator, and that's producing 2 to 3 meter high waves, which you would have in a normal, very extreme storm. Behind the waveboard are 6 big cylinders with pushing the waveboard back and forth with 200 bars of pressure. And those 2 to 3 meter waves go all the way through the flume, and at the end they collapse at the dike.
The two structures being tested today are dikes composed solely of clay. After 3 hours of this infernal pace, the team has to stop the experiment because the first damages already appear.
Now what you see is that over here, the grass layer is completely gone. And there's a gap of now currently 2 meters. We don't know how deep it is yet, but at least half a meter deep. But the question is, does it also withstand the full duration of the storm? And how much clay do we need for the dike to withstand the full duration of the storm, so that it doesn't break during the storm?
To answer these questions, Pim must repeat the experiment to test the resistance of these dikes to the point of failure. His conclusion is indisputable. The dikes of this type can only withstand the violence of the waves for 25 hours. Beyond that, the dike breaks down and the water could flood the land. Clay is therefore a solution to raise the dikes, but in the future, it will probably not be enough.
When sea level is rising further, we can further increase the height of our dikes. But if sea level really goes up more and more, you should also question if people still want to live behind very high dikes with a very big risk of a flooding. That might become unacceptable then, and then we might have to give land back to the sea.